Hello, I'm Dongwook Ghim, postdoc here in iTHEMS, and today I'm going to talk about renormalization under the title of this one, Renormalization Revisited at iTHEMS. Yeah, fortunately today it's March 14th, which stands for 3.14. Yeah, so this is the first leading numbers in pi, which is quite important in all of mathematics and physics and other sciences. And actually, I wasn't aware of this kind of fortunate match. Yeah, so I prepared my talk basically without acknowledging this. And yesterday evening, I realized, oh, it's 5 tomorrow. Yeah, so I deliberately made a connection with renormalization. I prepared and pi, and fortunately found a very nice one as stated here. And it appears, pi appears in the result of Gaussian integral, which plays a very important role in many physics, not just in high energy physics. So today, as a complementary approach or supplement to the Masazumi Honda's previous community talk in February, I prepare a bit about renormalization as an introductory thing. And I think this is the most important concept in modern quantum field theory and statistical mechanics, so we can learn something from this kind of material. So today I'm going to introduce two examples of renormalization, one in position space and second in momentum space. So in position space, I'm begin with the spin chain, which is defined as a set of spin degrees of freedom assigned to each side of lattice. So for instance, if we can think about one-dimensional lattice line, and each side contains a single spin, which can direct upside or downside. So let's parameterize this upside spin as +1 and downside as -1. Yeah, then we can assign number to +1 or -1 to each side of the lattice. And then think about some interaction or physics theory emerging from this setup. So many of physics theory is described by Hamiltonian. And if you think about the simplest but fruitful Hamiltonian, then we can think about this kind of Ising model type Hamiltonian. And it's made of nearest neighboring interaction between two neighboring spins, parameterized by coefficient k, and sigma I plus 1 stands for the spin assignment to the nearest neighbor sites. And H is kind of, usually this is called transverse magnetic field, but it's anyway not that, the name is not that important here. And sigma I stands for each site. So this means interaction between the nearest neighbor sites, and this is kind of reaction to the external perturbation or quench. And then if one can write down this Hamiltonian in terms of, smaller pieces, which is defined on this nearest neighboring site, then this is nothing but a decomposition of this summation into smaller pieces. To make things equal footing, I assign this coefficient of the linear term as h/2. Then to do some statistical thing, we usually think about so-called partition function. This is nothing but the sum of some special weight, which is called Boltzmann weight, over all possible configuration system can have. So here, all the configurations can be parameterized as spin, direction, +1 or -1. And then if there are n side spin, we have 2 to the n possible configurations. And each configuration, the Boltzmann weight is given by exponential to the -h. H is Hamiltonian. And here I set the temperature or inverse temperature beta to be 1. But yeah, so I think today's talk will not play a very important role, but somehow to do metaphysical interpretation of the result, dividing beta is quite useful. But let's ignore them for a moment. And then if you define this kind of quantity, all the other interesting physical quantities like energy or free energy or its variation like specific heat or such kind of physical observable can be derived from this quantity called partition function. We write down its name. So one of the most important business among statistical physicists is to compute partition function given this system. Yeah, anyway, this recipe is given here. Then what we need to do is to compute this kind of thing, summing over all the possible configurations. But usually, if you think about many body, n to the order 5, say, then counting all the configurations sometimes very difficult. And practically we need to consider n to be 10 to the 23, like order Avogadro number, then counting all configuration is almost impossible. So renormalization come up with this at this kind of situation. So let's decompose this summation over all possible configuration into two pieces. So one is summation over all possible odd side spins configuration, and second is summation over possible configuration at even side spin. Yeah, this is nothing but splitting the sigma into two different sigmas. And then doing this piece first. Yeah, graphically, this is doing this and this side. Yeah, doing averaging over this side and this side, even sides first, then reconstructing effective new system made of both this side. Yeah. Then here in the beginning, we came up with original Hamiltonian. But my goal is to think about another system made out of original system, which Hamiltonian is given by H prime. And people, consider this kind of thing because when we zoom out this kind of system, the important features still remain, while unimportant feature will vanish as we repeat this kind of zoom out procedure, zoom out process. Yeah, anyway, the remaining thing must be written down vigorous freedom defined at all sides, which is surviving here, right? This way. And all at every odd side, at every neighboring set of odd side spins, we can define we hope we can still define local Hamiltonian given by this way. And the remaining puzzle is to make a conjecture for the form or the coefficient appearing in this new Hamiltonian. Yeah, so remaining thing is the tedious computation. So again, this partition function looks like this way, and each vector can be written this way. And what we need to do is to sum over the middle spin, sigma I plus 1, which is defined here, leaving these and these survive. And then, what we need to do is to compute this Boltzmann weight and take the summation. And then by taking both sides, we end up with, on the left side, this one, and on the right hand side, which is quite complicated. Yeah, but anyway, here, if you look at this expression, there is a common piece. This piece and this piece, which emerges from the linear piece, transverse magnetic sum, is common, so we can vector out. And the difference thing is this one, this one, this one, this one can be again vectored out. And by combining this linear piece this way, and combine this piece this way, then we end up with this. Yeah, this is just a small algebra. And by taking small h, small transverse magnetic field limit, then we can compute this kind of U effective Hamiltonian. Yeah, but recall that original Hamiltonian was given by this kind of quadratic term plus linear term. Yeah, but here, unfortunately, we end up with tangent hyperbolic, which is very ugly, and low cosine hyperbolic, another ugly term. Yeah. Then by employing this kind of trick, and sigma I plus sigma j, sum over two spin sides can be either plus 2 when both direct the same upward direction, or 0 when both are aligned anti-parallel plus minus or minus plus, and when both direct the downside, the sum is minus 2. And by this kind of particular value nature of this sigma I plus sigma j, we can end up with, when there is an even power of the sigma I plus sigma j, it can be mapped to this kind of constant or quadratic piece this way. And when there is odd power, it can be mapped to this linear piece plus 2 to the third powers. Anyway, this helps us to making the tangent hyperbolic and low cosine hyperbolic simpler. Then we end up with either constant or quadratic or linear in the end. Then I plus sigma I plus 2, linear piece plus yeah. Now you can compare that kind of new Hamiltonian with original Hamiltonian. We called this quadratic coefficient as k and linear coefficient as h. Then this part can be mapped to new h over 2, and this part can be mapped to new k, yeah, over 2. So not over 2, sorry, just k. The new k can be given by this one, O cosine hyperbolic 2k, yes, and new h prime can be given by proportional to original h, but dressed with some k dependent.
Actually, in the original Hamilton, maybe each term is sigma I plus sigma I plus 1, right? In the original, this one.
Yeah, I plus.
No, in the last term.
Last term.
Yeah, there is only sigma I, but I think sigma I plus 1.
Yeah, but I made the weight as 1 over 2.
So,
so if you sum over all the I, then it will be okay, I think.
Yeah, okay.
Right, sorry, you're right.
Yes. I think, yeah, it could be, yeah.
Yeah, thanks for saying. Yeah. So anyway, the lesson of this exercise is by zooming over the system, we can end up with another system which has different strength of iterations. Yeah, but so if you think about kind of theory space, which is parameterized as by the value of h or k, not all the points of this spaces are independent. For instance, some space, some number can be connected by this kind of operation. And this kind of operation, zooming over or zooming in, can be, it's called renormalization. Yeah, so basically what renormalization does is by changing the scale of the system, it connects many different theories, which can be located at a certain point in a parameter space. Yeah, that's it. So for instance, what we can do further is to analyze the fixed point analysis of this kind of transformation, right? And then there might be some special point which appears as a fixed point under this kind of transformation, and people call that kind of theory as a conformal field theory, or people give us some non-trivial name to that kind of fixed point. And it is important because it can appear many different places in the experiment by integrating out anyway by averaging over minor details of the theory. It contains surviving important feature of the which many different theories can share. This is one exercise with position space, and let me go to the momentum space side. And there we can face pi. Position space can be basically integrated out or average over one even side spins. So the lattice constant A gets twice larger for this kind of step. And momentum space, we do something different. So consider momentum coordinates, something like this. Then think about shell whose radius is AC, the central curve. And then what we do is consider, basically we need to do what we need to do is to compute the partition function D, which is defined as a path integral. If we think about field theory, this one. So this can be kind of generalization of this kind of discrete partition function sum to the continuum. Then what we need to do here is to decompose this phi into 2 degrees freedom. There, on position space, we decompose degrees freedom into odd and even size. But here, we consider low momentum and high momentum degrees freedom. So this stands for momentum is smaller than certain value, and this stands for momentum is larger than certain value. And we can decompose this action thing into 2 different degrees of freedom, and also measure can be decomposed into 2 bits this way. And likewise, there we do some calculation for even size first, and here we do certain calculation on this higher momentum size first. This is so-called integrating out higher momentum. Then this will be moved, and we end up with the new effective action, which only goes up by small. Yeah, like the Kadanoff decimation case. Sorry, this kind of averaging over certain sites technique. This kind of technique is called decimation, and this kind of splitting momentum degrees of freedom and integrating out higher momentum degrees of freedom is called momentum shell renormalization. Yeah, and we end up with a new theory with different coefficients assigned to each term involving phi low momentum. And this is too sketchy to other people who's not working on high-energy physics or statistical mechanics or condensed matter. So I prepared one simple exercise with Gaussian interval. Yeah, let me finally visit. This exercise stands for, let me, This is 2 pi. Right. Yeah, but this is quite boring. I mean, this is interesting enough. Yeah, but there is no physics further we can discuss. Then let's introduce small interaction between the two. So now what I want to do is not just measuring this part, ordinary Gaussian integral, which is only depends on either x or y. So we can do x part and y part separately, and we can end up with this number. But with this kind of x squared times y squared, there is no closed formula, I hope. Yeah. And so here, there are so many strategies, but yeah, to the ordinary person like me, I think I can try something simpler. So if we carefully see this term, this can be combined into this way. Let me write down just arguments in the exponential function. And see, here we have Gaussian integral y squared, but with, contaminated with something else. Yeah, but anyway, if we ignore x integral, then we can do y integral first. Then it's still a Gaussian integral, so we end up with, so there still remains x integral this way, but some portion can be done this way. And one can really expand this weird unwanted term into x. This is nothing but Taylor expansion, and map it and move the pieces into the inside of the exponential. We end up this kind of series in the end of exponent. Yeah, here what we do is just measuring certain interval, but I will show this can be interpreted as kind of renormalization in the physics literature. Because if you look at this momentum kind of approach, we have 2 degrees freedom, low momentum and high momentum. And we do certain operation on the high momentum side, and then leave low momentum side later. And then if you look at low momentum effective action, which is the remnant of the higher momentum modes, then we can interpret this kind of action as addressing, self-energy or wave function renormalization, and many other interactions appear out of renormalization or integrating out unnecessary degrees freedom. So, yeah, for instance, this kind of thing can also have diagram interpretation. The self-energy can be expanded with diagrams like this. Later, I realized that this kind of diagram gives wave function normalization, not mass, not rest mass. But anyway, let's call these are all low momentum modes. The internal line appearing here and here, there are higher momentum. Yeah, this gives originally low momentum particle propagates this way, simpler way, but its propagation can be dressed or can be affected by hidden degrees freedom, what we call higher momentum modes. So this way, and this kind of diagrammatic expansion can be done forever. And by summing over all the infinite diagrams, we can end up with effective theory, which describes low momentum modes. Yeah, this is diagram interpretation of this kind of effective action feature or path integral feature. And here, I want to address this issue by changing the integral Gaussian integral slightly. So if we change the coefficients of Gaussian integral, let's call this as m squared, and let's call this as m large m squared. So here we have 2 particles whose name is x, and another's name is y. And x particle carries a small mass m, small m, and y particle carries large mass, capital M. And their interaction is governed by this kind of 4-point interaction given by quadratic term of x and quartic term of x and y with epsilon coefficients. And when epsilon is very small, we can justify my naive integral procedure and consider new theory out of x particle only. Yeah, then if you carefully follow the coefficients, small m and large m, this way, then we have m here and 2 pi there, and we have small mass here. And here, you can see mass of x, small m, is dressed with this kind of additional factor. So, and in the end, what we are going to do is to call this kind of extra coefficient in front of x squared as renormalized mass. Renormalized is the original mass we call bare mass plus certain correction. And this correction proportional to the epsilon parameter, which is parameterized the interaction strength here. And this is a way to consider interaction of many different species in the nature with the tool of renormalization. So, yeah, that's it. Yeah, this is the end of my calculation.
Okay, thank you very much for very illuminating talk. Okay, questions?
You took small h limit.
Small h limit.
H is the external field.
Yeah. In Kadanoff's machine.
And then you get some maybe exact result. But for finite h, it is difficult to derive some.
Oh, interesting question. The question was, even though I use small h perturbation in the Kadanoff chain case, whether I can compute general expression. Yeah.
Experimentally small h is more interesting.
I think so. And yeah, but I think it's not easy to get general expression higher h. Yeah, but small h expression is quite interesting because at h order 1, I mean, when h approaches to k, then interesting thing happens. Yeah, so I'm not sure whether all the interesting feature can be reflected in the approximation, yeah, but I hope some of them can be reflected. For instance, in 2 dimensions, we have different equation for the renormalization group. In 1D, we have k prime is 2 over log line hyperbolic something, saying 2k, something like that. But 2D, the coefficient gets different. So here, 4k makes the non-trivial solution to the this kind of perturbation. And yeah, I think that's already interesting phenomena captured in perturbation.
Thanks for your nice talk. My question is, for more complicated systems, how to tell which parts of the system are not important in your analysis, which can be removed or averaged?
That's another interesting question. I think one easy tool is to counting kinematic dimension of the terms, interaction for other terms. So in Heinz theory, when you because we have Lorentz theory and also space-time picture, we can assign scaling dimension to the operator easily, quite easily. And then we can say this term plays an important role in the end by looking at such a kinematic dimension, and this term is not. But this kind of argument is based on perturbation theory. So it has limitations, but anyway, it's very easy to apply.
Next, can you imagine and what happens if you have a positive sign or signature in the exponent?
I mean, changing the sign of mass square.
Yeah. One is negative, but the other is positive, something like that.
I see. Maybe mass square. Maybe I missed the square a lot. Interesting. Yeah, I think that stands for some unstable particle thing in stability. So if you flip this kind of thing, actually, this is kind of analytic continuation. This is not the measure of the interval, I guess. So in the end, it will lead another instability by changing the correct mass sign to the incorrect way. So originally this x mass was positive, mass square was positive, but if it's dressed with with this kind of ill-defined term, then it becomes negative, I think. So this makes the theory kind of ill-defined or unstable. But I don't have any deeper answer. Maybe, changing this expression, integral expression to the closed form can be revisited in another tool like resurgence. Yeah, but I'm not sure. Okay.
Well, Dr. Honda emphasized something like the knowledge of unknowns or like that. From your viewpoint, how do you understand the Honda's viewpoint?
I think so. In this momentum shell approach, I basically got rid of this higher momentum modes, or in train example, I got rid of even size degrees freedom. So getting rid of such a degrees freedom or averaging over such a degrees freedom has meaning in terms of that ignorance of certain nature. So in the end, what remains is okay. We interpret the remaining thing after this kind of integration or average as an important nature of the system. And
But in your case, everything is formally incorporated. That's your viewpoint, right? And
right.
Dr. Honda's viewpoint is something like cut off and unknowns like that.
Yeah,
But
but still
that
we
can be made. Yeah.
Yeah, we can go against this flow. So here I assumed we know everything originally, then we lose certain information, right? Go down. Yeah, but we can introduce additional assumption in the first line expression and then see what happens. So that's related to, I think, relevant or irrelevant of the certain deformation. Yeah. Anyway, we can do this kind of, we can repeat this kind of exercise with several different type of original actions, original terms, and then see which type of information is important in the end, and which type of information is not important, say irrelevant in the end.
Oh, I see. Well, but some people say that your viewpoint is something like the non-perturbative analysis. And Honda's approach may be perturbative in essence. That's not the correct assessment.
Yeah, I think we can say so. But even though I said this kind of thing in an unperturbative manner, but when we like something to do precise with number, then as I did this way here, this is basic perturbation in the end. I expand things in terms of epsilon over m squared, right? Yeah, so even though this framework looks non-perturbative, what we need to do in practice is almost every time is perturbative.
Okay, thank you.
Thank you.
Any other question? If not, let's thank Dongwook Ghim again. Thank you very much. Okay, any further announcement?